Hello class. Give me just a minute while I get my laser activated. Alright, and we are good to go. So we're going to go over the first section of Unit 1. So to start, let's just do a simple definition of statistics. Statistics, and you can write this down in your note sheet. Statistics is the science and art of collecting, analyzing, and drawing conclusions from data. I'll say that again. It is the science and art of collecting, analyzing, and drawing conclusions from data. Now, very important to the enterprise of statistics will be the notion of variables. So briefly, what is a variable? A variable is any attribute that can take different values for different individuals. A variable is any attribute that can take different values for different individuals. So let's look at an example of a single, emphasize that, a single variable. That would be, for example, dragon species. So perhaps that's the variable that I'm interested in. Right, so I go to Romania and I want to study the dragons that are living in Romania, and in particular I'm interested in the different kinds of species that populate Romania. Alright, so that's the attribute I'm interested in, and that attribute, as your definition states, it can take on different values. So the various values that I come upon while studying dragons in Romania is that some of the dragons are Norwegian ridgebacks, some of them are Hungarian horntails, some of them are Swedish short snouts, and some of them are Chinese fireballs. Right, so what we have here is, again, a single variable, and that's dragon species. These, Norwegian ridgeback, Hungarian horntail, etc., those are different values that attribute has in the different dragons that I come across. But this is just one variable. And this will become really clear once we do more practice with this. Let's look at another variable. This one is going to be Furby weight. So if you don't know what a Furby is, just go ahead and Google it whenever you have free time. It was a horrible craze that happened during the 90s. So we have these different Furbies, which are just basic, ugly, fuzzy animals. And so I come across a number of Furbies, and I'm interested in what their weight is. So the first one I come upon weighs 1 pound. The second one, 1.5 pounds. The third one, 1 pound again. And the fourth one was 8 pounds. All right, so I want to, again, focus on the notion of a variable. Here we have one variable, which is Furby weight. And these are the different values of that variable among these different individual Furbies. Okay, and to help remember the word variable, it's related to the word vary. So just as the weight varies from one Furby to the next, so a variable will vary from one individual to the next. I also want you guys to notice that Furby weight is a very different kind of variable than the kind of variable that we just were dealing with. So, for example, notice that Furby number 4 weighs 8 times as much as Furby number 1. All right. Now, that ability to compare in a numerical way, this one is 8 times as heavy. So we know how they relate to each other numerically. We don't get that in every single variable. So, for example, consider another variable. Say I am studying the different species of angels. All right, and the first angel I come upon is a throne. The second one is an archangel. The third one, we have another throne. The fourth one is a seraphim, and so on. Now notice that with these angels, it doesn't make any sense to say that angel number 4 has 8 times as much angelity as angel number 1. That doesn't make any sense. On the one hand, we can say that Furby number 4 has 8 times as much weight as the first Furby does, but we can't numerically relate angel species. Right? And that is because angel species is a different kind of variable than Furby weight is. Furby weight is known as a quantitative variable. Right? You might want to write down the definition of a quantitative variable in your note sheet. A quantitative variable takes number values for which it makes sense to find an average. Okay, so I'll say that again. A quantitative variable is a variable that takes number values for which it makes sense to find an average. All right, so we could have the average Furby weight, but we're not going to find out the average angelity or angelness. All right. So angel species, that's going to be an example of a categorical variable. All right. Categorical variable is a variable that assigns labels that place individuals into particular groups or categories. I'll say that again. A categorical variable assigns labels that place individuals into particular groups or categories. All right, so let's do a concept check on this. All right, so here I'm looking at various cars in a car lot, and I'm taking note of both their car type and how much they cost. So here I show the different car types I came across. There were DeLoreans, Lamborghinis, Batmobiles, and Ford Pintos. And the average cost of the DeLorean was $75,000. Average cost of Lamborghini, $350,000. Average cost of the Batmobile was $10 million. And the Ford Pinto, according to legend, Ford knew that the Ford Pinto was dangerously flawed and could kill people, but at that point they had already put so much money into designing and producing Ford Pintos that they decided it would be more cost effective to just let it kill people and deal with the lawsuits instead of not sell the Ford Pinto at all. All right, so we'll just say that it now has an average cost of $0 because nobody wants to buy it. All right. So on your note sheet, if you could, tell me how many variables we have here. How many variables do we have here? Is there a categorical variable? And if so, which variable is a categorical variable? And is there a quantitative variable? And if so, which one is a quantitative variable? So go ahead and answer these questions. Pause while you're doing that so you can think about it. And then once you've answered them, then unpause and we'll discuss. Okay, so I'm assuming that you've answered these 3 questions. We have 2 variables. One of them is car type. The other is cost. There is a categorical variable. That would be car type. And there is a quantitative variable, and that would be cost. All right, let's do a second concept check. So in this one, we'll say that I'm going in the woods and I'm doing a exploration of the trees that are living there. And so while I'm exploring, I notice that there are 33 trees that are male oak trees, 23 female oak trees, 12 male redwood trees, 47 female redwood trees, and 20 male palm trees, 31 female palm trees. So, true or false? There are 6 variables that I explored here. All right. Okay, so the answer is that's going to be false. We have 2 variables. One of them is going to be the gender or sex of the tree, and the other one is going to be the type of tree or the species of tree that we're looking at. So we only have 2 variables here, not 6. All right, let's look at one more concept check. Let's say that I'm in a mall, and I'm just walking up to random people, writing down their name and what their zip code is. Now the question is zip code a quantitative variable or a categorical variable? All right. So go ahead and pause, think about it, and when you're done, unpause, and we will discuss. Okay, so I'm assuming that you have already figured out what you think the answer is. So in this case, are the values that are variable zip code takes on are numerical, seemingly. But this is not a quantitative variable. It's a categorical variable. And again, think of it this way. So Daphne has a zip code of 76054, whereas Scooby has a zip code of 76017, and Plotinus here at the bottom, he's got a zip code of 58273. All right. Does it make any sense to say that Daphne and Scooby are more zip codey or have more zip codes than Plotinus? No, that doesn't make any sense. So these zip codes are really just categories that happen to be spelled out with numbers as opposed to with letters. Zip codes really are just categories that are spelled out with numbers rather than with letters. So for example, we could think of, I'm new to Arlington, so I really don't know the zip codes here at all. But let's say that we have Northwest Arlington, and maybe it has its own zip code, Northeast Arlington has its own zip code, and Southwest Arlington has its own zip code. All right. Then all this zip code means is that Fred, in this case, he lives in Northwest Arlington. All it's telling you is what Fred's location is. So it's what is the category of his location? Which location is he in? All right. Let me give another example which might further help in understanding this distinction. So here we have different states. All right, Washington, Oregon, Idaho, Montana, Wyoming. Now what I could do is instead of having these abbreviations, I could just refer to Washington as 1. I can refer to Oregon as 2. I could refer to Idaho as 3. Montana as 4, and so on. Now, by doing that, have I made a person's state? So, state that you live in, that's a variable. So I could I could go around asking people what state they're from, and somebody could say that they're from Washington. Now when they say that, I just put a 1 in. Another person might say they're from Oregon, so I put a 2 in. So again, their state of origin differs from person to person, so that's going to be a variable. And I'm using numbers, but it's not a quantitative variable. People from Washington aren't the statiest of people. All right, there's no numerical relationship between people from different states. All right, they belong to different categories. They come from different states. So don't get confused on that. Just because the attributes of a variable are spelled out with numbers instead of letters, that doesn't necessarily make it a quantitative variable. All right, let's talk. This is kind of our introduction into analyzing categorical data. It's going to kind of be a little bit of an introduction to probability thinking in general as well. So let's say I have flipped a penny 4 times. Can you rank the 3 possible sequences below? So each of these sequences is a possible sequence. So maybe the first time I flip a penny, it comes up heads. The second time it comes up tails. Third time it comes up heads. Fourth time it comes up tails. That's one possibility. That's one possible sequence. Another one, though, is that the first 2 times it comes up heads, and the last 2 times it comes up tails. All right, so these are 3 different possible sequences. There's also other possible sequences, but we're just focused on these 3. So here's the question is, can you rank the 3 possible sequences below in order from least likely to most likely? So go ahead and think about that, pause the video, and after you've come to your conclusion, unpause and we will discuss. Okay, so I'm assuming that you are done thinking about it. Now, so the answer, yes, they can be ranked. They can be ranked, but they're all equally likely. If you thought that this sequence was more likely than the bottom sequence, then you have been the victim of illusion. All right, and we'll talk about that illusion. So this is the way to kind of think about the way probability works. All right, is when you flip a coin, there's 2 possibilities. One is that it lands up heads, and it'll do that 50% of the time. The other possibility is that it lands tails, and it'll do that 50% of the time. All right, now of this 50% of the time that it comes up heads, and I flip it again, 50% of that original 50%, it'll come up heads again. 50% of that original 50%, it's going to come up tails. So in other words, if I flip a coin 2 times, the probability that it'll come up heads both times is 50% of 50%, which is just going to be 25%. Or what's equivalent to 50%? 50% means 1/2, right? Half of the time. So what is 1/2 of 1/2? That is 1/4. Right. So it'll come up heads both times 1/4 of the time. Now the reason why I had this rectangle come up is because there's another way to think about this. What we have here are 4 possible ways that we can flip 2 coins. One way is that it's heads twice. Another way is that it's heads the first time, tails the second time. A third way is that it's tails the first on the first flip and heads on the second flip. And the final way is that it's tails on the first flip and tails on the second flip. So those are our 4 different possible sequences if we flip a coin only twice. Each of these 4 sequences is equally likely. One isn't more likely than the other. So what does that mean? That means that the probability of it being tails on the first flip and heads on the second flip, that has a 1 in 4 chance, or 1 out of 4 chance of happening, or a 25% chance of happening. All right, so these notes are basically just stating what I just explained to you. I put this in at this point. I think I'd be belaboring the point, but the idea was that how many times will the first coin flipped be a heads? That'll be, all right, these 2 out of 4 times. That'll be half the time, 50% of the time. Now, what percent of times will it be heads both times? Well, that'll be half of this half, or 1/4 of the time. 1 sequence out of these 4 possible sequences. All right, so let's do a concept check at this point. So what is the probability of flipping either a heads 2 times in a row or a tails 2 times in a row? All right, so I'm asking for a single probability here, not 2. What is the probability of flipping either both heads or both tails? Or another way to put it is, what is the probability of flipping the same side both times? All right, so that's the first question of this concept check. So take some time to think about what the answer to that is, and pause while you're doing that. And when you're done, unpause it, and we'll continue. Okay, so I'm assuming that you have already calculated what this probability is. I'll give the answer on this one. So on this one, it's going to be 50%. All right, because there's four possible sequences: heads, 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 tails, tails, heads, tails, tails. So those are the four possible sequences. Two of those sequences are heads, heads, and tails, tails. So 2 out of 4, that's 50% of the time. So 50% of the time you'll flip either heads, heads, or tails, tails. All right, now a similar question. What is the probability of not flipping the sequence first heads and then tails? So what is the probability of not flipping this sequence in particular? So take time to think about what the answer to that is. When you're done, unpause the video and we'll continue. Okay, so let's move on. This is kind of getting back to that initial question, all right? So we want to find the probability of flipping each one of these four sequences, all right? Getting heads 4 times in a row, getting heads, tails, or in this one, tails, heads, tails, tails, or 2 tails and 2 heads. All right, so before I even continue on, try and solve both A and C. See if you can figure out what the probability of getting 4 heads in a row is and what the probability is of getting tails and then heads and then tails and then tails. So go ahead and pause this, try and work those out, and then we will go over it together. Okay, I'm assuming that you have worked those out, so let's go over it. So one way to figure this out, I've kind of gone over a counting method of calculating a probability. There's another way to calculate probabilities, though, that I'll go over, and that's just multiplying the fractions. All right, so what's the fraction representing the likelihood of me flipping a heads on the first one? That's 1/2. How about flipping heads on the second turn? That's 1/2. How about flipping heads on the third? 1/2, and so on. So the probability or likelihood of doing 4 heads in a row is going to be equal to 1/2 times 1/2 times 1/2 times 1/2. That's just going to be, all right, if you multiply it out, that's going to be 1/16. So on average, every 16 times I flip a coin, or every 16 times I flip a coin 4 times. Every 16 times I flip a coin 4 times, on average there will be one of those where I flip the coin as heads 4 times. All right, so just to make sure we're clear, what I'm saying is I flip a coin 4 times, so now I flipped a coin 4 times once. Then I'll flip a coin 4 times again, so now I flipped a coin 4 times twice. Now if I do that a bunch of times, once out of every 16 times on average, I should get all heads. All right, so one way of calculating that probability is just by multiplying the fractions that represent the probability of each individual turn, each individual flip, each individual trial, however you want to think of it. Another way is, okay, so 1 out of 16, if you put that in your calculator, that equals 0.0625. So another way is just multiplying not the fraction, but the decimal that represents it. So 0.5, that's 50%. So what's 0.5 times 0.5 times 0.5 times 0.5? That's going to be 0.0625, the exact same thing that we got when we multiplied the fractions together. So you can either multiply fractions or you can multiply decimals. Decimals, remember, are the exact same as a percentage, except you move the decimal point over 2 places. So 0.5 is 50%, 0.05 would be 5% of the time, 0.02 would be 2% of the time, 0.2 would be 20% of the time. All right, so the probability of flipping heads all 4 times is 1 out of 16, or 0.0625, about 6% of the time. Now what about with C? All right, we have tails the first time, heads, then actually, yeah, we'll do C. Tails the first time, then heads, then tails, then tails. All right, we might think that that is more likely than getting heads all 4 times. All right, because it's only a 50% chance of getting heads or tails, so you should get a little bit of each, right? Well, wrong. It's going to be the exact same thing. All right, 50% chance of flipping a tails here, 50% chance of flipping a heads, 50% chance of flipping a tails, and 50% chance of flipping a tails. So it's going to be the exact same answer. Now, to make sure that this is perfectly clear, let's look at this again using what I'm going to call the branching method. All right, so here I've used the branching method. The first flip can be either heads or tails. All right, the second flip can also be either heads or tails. The third flip can be either heads or tails, and the fourth flip can be either heads or tails. All right, so what we can do is count these letters at the very end. So I'm going to do that. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16. That's 16 different possible sequences. All right, one sequence is heads, 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 heads. Another possible sequence is heads, 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 tails. So I'm not going to go through that for all of them, but what this shows us is we have 16 different possible sequences, and each one of them is just as likely as the other. So getting all heads is just as likely as getting heads the first time, tails the second time, heads the third time, and tails the last time. All right, those two different specific sequences are each equally likely, and they each have a 1 in 16 chance of happening, or 1 out of 16 chance of happening. Okay, so here's a completely different questions. All right, so again, I say completely, somewhat facetiously. We flipped a coin 4 times. What's the probability of getting only 1 heads during those 4 flips? What is the probability of getting only 1 heads during those 4 flips? So go ahead and pause, look at it, unpause, and we will discuss. Okay, I'm assuming that you have come up with your answer. So let's think about it. One way to do it using the counting method, all right, is we just see how many of these 16 sequences only have 1 heads. All right, so if you flip heads on the first time, then you cannot flip heads again for the rest of it. So that's only going to be 1 sequence, heads, tails, tails, tails. So that's 1. Another one is we flip tails the first time, then heads. Then at this point we can't do heads anymore. So it's going to be tails, heads, tails, tails. So that's another possible sequence. So we got 2 so far. Another one is we flip tails the first 2 times, and on the third time we get heads. And the last time, the last possible sequence, so the third one is tails, tails, heads, tails. So that's the third possible sequence. And the last possible sequence is tails, 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 then heads. So out of these 16 possible sequences, only 4 of them only have heads happening once. So what's 4 out of 16? Well, that simplifies to 1 out of 4. So you have a 25% chance of flipping heads only once during 4 flips. All right, 25% chance of flipping heads only once during 4 flips. I want you guys to do the same thing, use the exact same process that I did here. Count the number of sequences out of these 16 where there's only 2 heads. Not 1 head, not 3 heads, just 2 heads in the course of 4 flips, and figure out what the probability is of having only 2 heads in the course of 4 flips. So go ahead and pause, figure that out. Remember to write these on your note sheet, unpause, and we'll continue. Okay, so I'm assuming that you have worked that out, so we're going to go ahead and continue at this point. All right, let's do concept check number 6. All right, so I measure the distance of various Chick-fil-A's from my house. The distances are below. One Chick-fil-A is 2 miles from my house. Another one is about 5.5. A third is 8 miles, and so on. Okay, so here's the question. What kind of variable is the variable of distance? Is it a quantitative variable or is it a categorical variable? So go ahead and figure that out, and once you have, continue on with the video. All right, so let's say that we are assessing whether each flipped coin lands heads or tails. So if it lands heads, then we record heads. If it lands tails, then we record tails. So this is a variable. It's coin flip outcome. We can call it that, coin flip outcome. What kind of variable is coin flip outcome? Is it a quantitative variable or is it a categorical variable? So go ahead and answer that and come back and we will continue. Okay, so why do we care about any of this? So let's draw this to some real world situations at this point. So let me say right off the bat, don't commit the gambler's fallacy. Let's talk about what the gambler's fallacy is. So the situation, we're at a slot machine in a casino. The probability of winning at that slot machine is 25%. All right, so you'll win on average once every 4 times. You have played 8 times so far. You have lost every single time. So here's the question. You've lost 8 times in a row. On the next turn, are you more likely to win or to lose on the next turn? Are you more likely to win or to lose on the next turn? So go ahead and pause, think about it. Once you've thought about it, come back and we'll continue. All right, you are more likely to lose. In fact, you have a 75% chance of losing. The same chance of losing that you had when you played the first round, because your probability of winning is 25%. Even though you've lost 8 times in a row, the next turn at the slot machine, you still only have a 25% chance of winning. So here's a question. What is the probability of each of these following full sequences? All right, on this first one, you lose 8 times in a row and then win on the 9th turn. And the other sequence, sorry. So go ahead and think about how we could calculate the probability of this sequence. Go ahead and pause, try and think about how we would calculate it, and then come back and we'll discuss. Okay, so I'm assuming that you have thought about it. So the way that we would calculate it is the same way that we are calculating it with the coin. What's the probability of losing? 75%. So, or 0.75. Now I didn't want to write that out 8 times, so I just put to the 8th power. What that means though is we have 0.75 times 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 0.75. All right, so that's 0.75 to the 8th power times 0.25. All right, so if we multiply these decimals together, what we'll get is 0.025. In other words, we have a 2.5% chance of losing the first 8 times. Actually, hold on. This number actually isn't right at all. I put this into the calculator and it must have given it back to me in scientific notation. There's going to be some exponent here. This is a much bigger decimal. All right, so it's something like 0.025 times 10 to the negative 10th power or something like that. You can calculate it for yourself. It's not going to be 0.025. It's going to be 0.00000000025, something like that. All right, but that's how you calculate it, though. And then what about the sequence where you lose 9 times in a row? All right, so how we would calculate that, that's just going to be 0.75 to the 9th power. And again, this is going to be off by a number of decimals, but one thing to notice is that you'll notice that 0.075 is 3 times as high, 3 times higher than 0.025. All right, and that reflects the fact that this sequence right here, where you lose 9 times in a row, that is 3 times is likely, 3 times more likely to happen than losing the first 8 and winning on the 9th. This is much more likely to happen than this sequence where you lose 8 times in a row and win on the last one. Okay, so what's the gambler's fallacy? It's the fallacy that after you've lost a bunch of rounds in a row that you are due for a win. That is a fallacy. You are no more due for a win than you were at the very beginning. So don't think that just because somebody has just left the slot machine after having lost a bunch of times in a row, that that's a good slot machine to now go play at. It's not. It has the same probability of losing that it had at the beginning. Okay, so let's look at we're still dealing with a casino slot machine with a 25% chance of winning. We want to know what is the probability of losing the first round but winning the second round. All right, so there's 2 different ways that we can calculate this. One is just basically using our calculator and dealing with the numeric probabilities. So what's the probability of losing the first round? Well, you have a 75% chance of losing, so that's going to be 75%. What's the probability of winning the second round? Well, you have a 25% chance of winning, so that's going to be 0.25. Then we just multiply these together to get 0.1875. Now we can also use the counting method, working with our diagram right here. So this is going to seem a little counterintuitive, so just try to go with it, though. With the counting method, we see how many different sequences we have. So we have 4 possible sequences here, another 4, so that's 8 total, then 12, and then 16. So we have 16 different possible outcomes. How many of those 16 different possible outcomes include losing the first time, all right, losing the first round, but winning the second round? Well, here we have this one right here, so that's 1. We have this one right here. Oh, I'm sorry, hold on. I forgot to, I got to put my laser on. All right, so we have 1 right here. We have a second one right here, loss, and then a win. And then finally, we have this third one, loss, and then a win. So that's 3 possible sequences where you lose the first time, win the second time. So that's 3 out of 16. 3 out of 16, if you, or 3 divided by 16, if you put that in your calculator, that's going to equal 0.1875, just like we found before, or about a 19% chance of happening. All right, so this is going to be, let's go to the next one. This is going to be slightly different. So here we're asking about losing the first round, but winning the second round. Now let's think about winning the first round, but losing the second round. So now we're winning the first round and losing on the second round. So calculation, well, what's the probability of winning the first time on the first round? That's going to be 0.25. Probability of losing on the second round, 0.75. So we're multiplying those same 2 numbers together. I've just switched the order here, but of course that doesn't make any difference in the end product. Now the other way is doing the counting method. So here we'll count how many of these 16 ways do we win the first time and lose the second time. All right, here's 1, there's 2, and there's 3. Those are our 3 possible ways of winning the first time and losing the second time. So that's going to be 3 out of 16 again, and that's equal to 0.1875. Now some of you guys might be confused because you're saying these aren't really different sequences. Like here we have winning first and then losing second. But here we also have winning first, losing second. And here we also have winning first, losing second again. So 3 different sequences that are all the same. I get it. Just remember that we have to think about it this way in order to account for the fact that we are 3 times more likely to lose than we are to win. So in order to account for that, we kind of count these sequences where you win the first time and lose the second 3 different times in order to make note of the fact that this is 3 times more likely to happen than winning both times. Okay? So let's do our concept check number 8. So again, casino slot machine, 25% chance of winning. What is the probability of losing both rounds? So on your note sheet, please write out how you would calculate that just using decimals. And then also tell me what the fraction is using the counting method. So go ahead and pause, work those out, and then unpause and we'll continue. Okay, let's do one last concept check, concept check number 9. So let's say, forget about this branching method diagram that I have right here. All right, let's say that we're at a different slot machine. This one has a 60% chance of winning, 60% chance of winning each trial. So how do we represent this using the branching method? I want you to try and think about how we would represent that using the branching method. Just as a clue, remember that 60% is equal to the fraction 3 over 5. If you're ever not sure which fraction to use, you can always put, in this case, this is if this is 60%, then put 60 over 100. Actually, don't worry about that right now. Actually, don't worry about that right now. Just know that this probability or this percentage simplifies to 3 over 5. All right, so find out, try to draw the first two trials on this slot machine. All right, so you'd play it twice. How would you represent those 2 turns using the branching method if it's got a 60% chance of winning on each given turn? And after you've done that, then try to calculate what the probability of winning only one of 2 rounds using the counting method. All right, so that means that you might win the first time and lose the second time, or you might lose the first time but win the second time. So both of those would be cases of winning only one of 2 rounds. So what is the probability of winning only one of 2 rounds using the counting method? All right, so go ahead and work that out, and that is the end of the slideshow though.